Today we are going to talk about blast furnace operations optimization. As we all know, optimization iron making operation under diverse technical constraint becomes a challenge for all operators. So today we will explore the strategies to optimize blast furnace operation, focusing on improving efficiency and productivity under various technical constraint. And constraint basically can be from coke to fluxes to blowing parameters and all. So let's dive into the key factors that drive these improvements. So as you can see, these all three segments where first of all we will like to discuss on especially three factors, and out of these three factors permeability and alkali input for optimal blast furnace performance is supposed to be the topmost agenda because both are complementary to each other. As we must be knowing that if alkali input increases, then crumbling of coke will be higher, as well as we will have to add on top up more fuel, also result in higher slag volume and lesser production. At the same time, crumbling of coke will lead to a permeability issue as well. Hence, in order to maintain a good permeability is really a huge enabler for running the furnaces in a better way. Now, in order to have a good permeability, we need also to go through a narrow size range of for raw materials with minimal fines. That is around thumb rule, we can say that should be less than 3% and all below 5 mm sizes. That is 5 mm sizes which are minus 5, that should be below 3%, and after screening in the stockhouse. Okay, so now coming to this also about alkali, uh, I would like to say that we must control alkali input, particularly zinc, which should be limited to 100 to 150 grams per ton of hot metal. And this numerical figure is very important because unless until we know that what is the limit, it is difficult to take action. So we must have to confine our limitation to 100 to 150 gram per ton of hot metal. Now, excessive alkali can damage, we know, it can damage the refractory lining and disrupt the processes in a huge manner. So, a typical limit of 1 to 1.5 kg per ton hot metal is enforced, and which is just mentioned the slides also, in order to have a aid in memory while day-to-day operation of the furnaces. Now coming to the iron content in the batches, I would like to say that uh, let us see the iron content in the batches should be optimal because high iron content in input material directly impact the efficiency of furnace. As you know that our lesser production of slag leads to a better improvement in coal injection and driving of the furnace, which is one of the very big enabler in obtaining higher production and productivity. Then reducing the need of excessive coke is also taken care by higher iron content, and this all result into improving the output. So this sets the stage for the specific optimization. So we will discuss in the following slide. As you can see that slag content reducing the slag content, what is supposed to be a powerful lever in optimization of the furnace operation. So, as I have already mentioned, that optimizing the slag rate could able to achieve a higher injection rate very comfortably. Thus, we can say that by decreasing slag by 10 kg per ton hot metal, we can reduce coke consumption by 0.3%, 0.3%, and boost productivity by 0.6%. So, this sensitivity is to aid in memory in order to uh, ease in calculating or day-to-day furnace operation, relating the fuel rate or the production productivity or the cost benefit analysis. This can help, and we can say that this reduction minimizes energy waste and enhance furnace throughput, making it a key focus for operation efficiency. Now, scrap addition is supposed to be also one of the huge enabler, and we can say that equal amount of almost fuel which is going to be replaced with the addition of scrap. Uh, so, pure metal additive increasing the use of scrap additive with 100% iron content by 10 kg per ton of hot metal yield similar benefit. So you can say that this adjustment lower the cook consumption, as I have already termed. This adjustment help in reducing the fuel rate overall. And in terms of cook rate, if we relate, then we can say that the 0.4% decrease is there with addition of 10 kg per ton hot metal, and which consequently gives us a productivity benefit of 0.6%. So using high purity inputs helps streamline the smelting process and improve overall performance. Coming to the part of a limestone, I would like to say that limestone consumption is another critical factor. While a specific data may vary, optimizing limestone use directly affect the slag formation and the furnace efficiency. And once the slag formation is a crucial role in obtaining all the economics indexes of optimal value, like cost on time, and which consequently depend on the slag viscosity, and which further is also depend on the basicity, and basicity is to be monitored as per the desulfurization potential of the slag. That is, this will be decided by the type of a feedback feedstock that is to be supplied for BOF. So these all decides that what sort of limestone consumption is to be maintained, and what sort of basis it is to be aimed at blast furnace. So by carefully managing limestone input, we can further reduce coke uses and maintain a stable operation, because this is very critical. So now coming to the effect of coke, we can say effect of coke or properties of coke quality plays a significant role in blast furnace performance, and as these all we can come to know by help of all these bullet lines. That is, reducing gas content in coke by 1% cuts coke consumption by 1.3% and increase productivity by same amount. Similarly, lowering sulfur content by 0.1% has varying impact, and depending on initial sulfur level also. And for instance, at 0.05% sulfur, coke consumption and productivity improved by 0.18%. So at 0.01% sulfur, this improvement rise to 0.71. So these gain highlight the importance of high quality coke in efficient iron making. Coming to the coke strength, which is itself is a very important property that is to be maintained by the blast furnace operators. So coke strength uh, is important in terms of their micum value. So increasing the micum 25 coke strength index by 1% reduces coke consumption by 0.6% and boosts productivity by 0.6%. So we can say that, and further we can say that there is a relation of strength versus CSR, where a 1% increase in CSR yield 0.7% improvement in both metrics. So we can say that reducing wear susceptibility measured by micum 10 value by 1% result in a significant 2.8% decrease in coke consumption and a matching productivity increase. So this is how the things getting related. So a stronger coke ensure better furnace stability and efficiency. This what is the message from this slide very strongly. Now coming to the hot metal composition, you can say that the composition of hot metal itself is a key optimization lever. So reducing silicon content by zero point 0.1 lowers coke consumption by 1.2% and increase by 1.2% benefit goes to productivity. So for manganese, the impact depends on ore manganese content. For ore with 30% manganese, a 0.1% reduction in manganese content cuts coke consumption by 1.17%, 1.17% and boosts productivity by 0.22%. So for 15% manganese ore, for 15% manganese ore, this figure improved to 2.27% and 0.44% respectively. So these adjustments fine tune the smelting process for maximum efficiency, we can say. And now coming to the most important aspects of the blast furnace operation is about the blast furnace parameters, which influence very significantly the performance of blast furnace. So we can say increasing the blast furnace temperature by 10 degree in 800 to 900 degrees centigrade range reduces coke consumption by 0.5% and increase productivity by same amount. So in the 1300 to 1400 range, these improvements are 0.22%. So on a higher range, our mm, these improvements becomes compared to lesser from the earlier. So oxygen content also matter. Below 25% coke consumption and productivity both increase by 0.25%, while above 35% they rise by 1.4%. Similarly, natural gas injection further reduces coke use with a reduction of zero point 0.8 kg. So this is the overall sensitivity for the operators.